So we'll start with this data visualization part. So in this, we're gonna explore the two libraries for the data visualization. One is Matplotlib, the other one is the Pandas. So Pandas, using Pandas also you can do the data visualization, and Matplotlib is specifically for that purpose. Matplotlib.pyplot is specifically for that purpose. Okay, so we'll be discussing both the things. All right. So I've just imported this required libraries. NumPy is to generate some synthetic data kind of thing. I've imported NumPy. Pandas is for this. This is also for the data visualization in this context. And then I've imported this matplotlib.pyplot and just named it as a PLT. All right. So one of the things that we are interested to plot or visualize is the curve plotting, isn't it? So something like this, as you see in this figure, right? So how to do these kind of plots, right? So for this, I've generated X, 50 numbers, which is in the range of 0 to 5 with equal line space. So line space function we have seen yesterday, right? So it generates 50 numbers with equal distance between them, equal space between them, in between 0 to 5. All right, this is our X. So now for the curve plotting, you need the two axes, right? X-axis and the Y-axis, X coordinate and the Y coordinate as well. So this is the X coordinate, Y coordinate is the cos of X, right? So cos of X, sin of X, two different curves we are going to plot. So np.cos of X, which gives you the cos of this X, whatever that have been generated, right? And similarly, sin of X will give you the sin of X. So this is the 50 numbers. So 50 numbers cos of X will be computed. 50 numbers sin of X also will be computed. Now we are plotting this X versus Y cos. I'm just indicating this with red color dashed line. So the first letter indicates the color, and the second, whatever the present here, which is indication of the line style. Line style, if you give only one hyphen, then it is a solid line. If you give two hyphens, there is a dashed line. Like that, there are different line styles. So like this also you can mention, there are some parameters, for them also you can pass them. Okay, so the various options that one can explore, like how to set the line width. I've given you the links in this file, you can explore them. Various options are there. So change of color, change of line style, change of the width of the line, like that, various options one can explore, right? So this is indicated with a red color dashed line, the cos function. Then another one is X comma Y sign. By default, there is some style default color it will take if you don't mention anything here. Right. So these are the two plots that we are plotting here, and we are giving the labels for the x-axis as well as the y-axis also. So the x label I am giving as x, just x. Y label I am giving it as a y. And the title of the plot is sine and cos curves. All right. So that's all. Execute this. Let me execute this first. Okay. So execute this. You will get a curve, something as it is shown in this figure, right? So like this. So this cos curve is indicated with the red color dashed line, as you see there, and the sine curve is indicated with a blue color solid line. All right. So like this, you can plot the curves. Okay. So suppose if you want to plot them as the points, not just the curves, right? So then we use the scatter function for plotting these points. So if you want to plot the points in the two-dimensional space, you can call the scatter of x comma y cos. Okay. So this x is randomly generated here using the normal distribution. 100 numbers we have generated here. This random means normal distribution, and we give it to the cos function. So we scattered this x and y cos, and it looks something like this, right? So as a points in the two-dimensional space. Okay. So then, are you following? Is it okay, or should I go slow? Little bit so. Is it okay? This phase is okay, right? Hello, everybody.
So,
I think you have to can go slow, sir.
Little slow. Okay, fine. So till now it is okay, right? I need not repeat that, right?
Yes, sir.
Yeah, yeah, fine. Okay, fine. So using the panels, like suppose I want to plot the subplots. Like here, if you see the curves, both the curves we have shown in the single graph, right? What if you want to show them in two different graphs and you want to show them like the subgraphs of the whole figure, right? So how to do that? Like you see this, something like this. Okay, so there are two different graphs within a one graph, right? So how to make this kind of plots? We use panels for this purpose. We use the concept of subplot. Okay, so the same thing I'm generating here, the same data I'm generating here, 50 numbers in between 0 to 5, and then this x is given to the cost function, output is y cos, this x is given to the sine function, the output is y sine. So now x and y cos one graph, x and y sine is another graph that I want to plot. Okay, so here I've generated a subplot of, I'm generating a grid of 1 by 2, 1 by 2 here, in which the first plot we are giving here. So the first plot is this x comma y cos, indicated with a red color dashed line, right? So here in the subplot, this 1 by 2 means you're creating a grid of 1 by 2. 1 comma 2 means so creating a grid of 1 comma 2. And this one specify the position of the current plot within that 1 by 2 grid. So this is the position of the current plot within that 1 by 2 grid. So first position. So that is x comma y cos is in the first position in that 1 by 2 grid. Similarly, the cos is in the second position in the same grid. Okay, so when I execute this, you can see this, right? So this is a 1 by 2 grid, one row, two columns. In the first column, we have the cos function. In the second column, we have the sine function. Similarly, you can create a grid of any dimension. Let's say I'm just creating a grid of 2 comma 2. Okay, so in that case, you will have 4 positions, right? So row major order, if you take, the top row is the 1 and 2 positions, bottom row is 3 and 4 positions. Okay, so if I give 1 and 2 positions only, it will be taken at the top like this, right? Suppose if I give 1 and 3 positions, one will come below the other one, right? One will come below the other one, something like this. Okay, so do you feel the difference? Hello? Suppose if I give 4 here, then it will come like this. Okay, so this 4 indicates the position. So this is the first position, this is the second position, this is the third position, and this is the fourth position in the 2 by 2 grid. All right. So is that okay? Shall we move on?
Yes, sir.
Yes. And these are some of the references for further personalizations, customizations. So if you want to change the line colors, line styles, colors, markers, anything, so you can follow these links and you can customize it further, right? So there are various options there, so you can explore them. Okay, so we'll also see the scatter plots. So we have seen one of the scatter plot already. Similarly, we'll see some other scatter plots. How to scatter the points group wise also we will see. So according to the group, can we assign different colors and the different styles based on the group to which this point belongs to, right? So for this purpose, we are importing make blobs dataset. So we have to generate synthetic dataset make blobs. So before we're gonna see that, as we got this package here, let me explain a bit about this package. sklearn. sklearn is the scikit-learn library, which is for the learning problems, like machine learning problems, to implement the machine learning problems. Very well documented library and very useful library as well. So if you want to know more about this scikit-learn library, as it is well documented, you can just type sklearn in the Google and click on the very first link, sklearn.org. Then you will see this, what are the different problems that it is solving, and different algorithm in each of these problem. Like you see that classification, regression, clustering. Suppose if I want to implement SVM, click on this. So you see that the complete explanation about the SVM, and then with the example also demonstrate how to implement this SVM, right? So it is very well documented. Not only that, it has got this machine learning methods. In addition to that, everything that is required for the implementation is also present in this library. Like for example, it has got the data sets, it has got the evaluation metrics, it has got the pre-processing techniques. So all those things are present at this sklearn library. That's the beauty of this. So for example, if I want to import the data sets, so all the data sets are presented sklearn.datasets, sklearn.datasets. So you can just type sklearn.datasets and click on the very first link. You see that there are different kinds of data sets. So data sets, if you see here, there are toy data sets, there are synthetic data sets, there are some real-time data sets. You see that. So all these are the toy data sets, all these are the real world data sets, generated data sets, and other kinds of data sets. Okay. So you can even generate the synthetic data sets using the functions available in the sklearn.datasets. Okay. So in addition to this, it has also got the evaluation metrics. So once you implement the method, to evaluate the performance of the model, we need some evaluation metrics, isn't it? Hello, am I right? To evaluate the
Yes,
performance
sir.
of the model, we need evaluation metrics, right? So those evaluation metrics are also present in this sklearn library. So sklearn.metrics you type, click on the very first link, you will be able to see all the evaluation metrics for the model evaluation. So like you see, here are the evaluation metrics for the classification problem. All these are the evaluation metrics: accuracy score, balanced accuracy score, F1, precision. All these are the evaluation metrics suitable in the context of the classification problem. And all these are the evaluation metrics suitable in the context of this clustering. And these are the keywords that we're going to use, it coming, right? So here are the keywords. So the keywords we're going to use in some of the functions. So just note this point. Okay. Similarly for the regression problem, right? So regression problem also we have this evaluation metrics, and these are the keywords: neg mean, absolute error, neg mean, squared error, like that. All right. So now, and it has also got the pre-processing techniques. All the pre-processing techniques are present at sklearn.preprocessing. sklearn.preprocessing. So how to pre-process the data, various pre-processing techniques. Okay, standardization, mean removal, variance, all that. Okay, so you can explore all of them. We're gonna implement all these machine learning models using the scikit-learn library only. Anyhow, we'll be exploring it completely. But just to give you an introduction, because we have seen that there in that program, right? So because of this, I have gone to that part. Okay, so coming back to this, so here we are generating the data set from sklearn.datasets. I've imported blobs dataset. Make blobs. Blobs is like, you know, that this kind of thing. One blob. There are 3 blobs in this. Okay, so 3 blobs with 3 different centers. Okay, so we want to generate that blobs kind of data set, right? So the data set I'm generating, I'm calling make blobs function. The number of samples that I'm generating is 100 with the number of features equivalent to 2. It means the number of attributes or the number of dimensions is 2 and number of centers is 3. With 3 centers, we want to create 3 blobs. This random state is something like you need not do it. It's like optional. Random state, if you fix the random state, what happens is that every one of us will get the same random generation of the data. Same kind of data we will get. So if you don't fix the random state, each one of us will get the different state because of the randomness of generation. Randomness in the generation of the data set will get different data sets. Because it's a demonstration, so I've just fixed the random state, but in general, you need not fix the random state. Okay, so I hope you're following. Following, right? Yes.
Yes, sir.
Yeah.
Sir,
Yeah.
what is blob? I just missed out.
This is this kind of thing, madam. Blob means one group kind of thing with some center. So this is one
Cluster.
blob.
Okay.
Yeah. Yeah. Yes. Yeah. So in the data set, we have this feature vectors as well as the target values. Target value indicates to which group, to which blob this point belong to, right? So there are three blobs, right? So to which blob this belongs to is indicated with a Y, right? So data set of 1 is indication of the target value, and data set of 0 is the coordinates that we are getting. So in this, there are two dimensions, right? So x1 and x2, two features are there, right? So we generated two features, right? So we're just plotting them group wise. Okay. So here I'm taking x y equivalent to 0, comma 0 and x of y equivalent to 0, comma 1. So it means basically you're trying to access all the points to wherever all the indices, wherever this wherever this condition applicable, y equal to 0. It means you're considering all the instances that belong to blob 0 or group 0, right? So this is the index number and this is the column number. So this is the index number. Your wherever this y equal to 0 is true, it means all those instances, those belong to group 0, those indices will come here. Index number comma 0 means the first x1 coordinate or the first feature of that you are accessing, and this is the second feature of that, right? Second feature of that. So this is indicating that, and these points are indicated with the yellow color squares. So in this, the first letter indicates the color of this color that you're giving to these points, and the second letter indicates the shape that you're giving to these points. So Y means yellow, S means square, yellow color squares, and you're just labeling them as a group 0, right? Similarly, you're plotting all the points that belong to group 1 with a magenta color stars, right? So this is group 1. So you will get all the indices that belong to group 1. Similarly, here you are plotting all the group 2 instances and giving the color of red color diamonds, all right. And we are also placing the legend indicating that which point is belong to which group, right? And this legend we are placing in the lower left corner, and number of points that we want to place in the legend is 1, okay? And we are also setting the y limits and the y ticks, x ticks as well. Okay, so y limit is set to -2 to 10 range, and x ticks, y ticks also we have given. And we have also given some annotation indicating that what that is, right? So like for example, here we have given annotation for the squares at this position of -10 comma 2, and at the position of 0 comma 2 we have given annotation of the stars. At the position of 8 comma 4 we have given annotation of the diamonds. So now you see the figure, you'll get the clarity. You see that the squares are indicated with yellow color squares, and the second group is indicated with the magenta color stars. Third group is indicated with the red color diamonds. So this is the legend that I was talking about, which is placed at this lower left corner. And you see that x ticks and y ticks are according to what we set, and y limit also we set -2 to 10, right? And these are the annotations that we have given. Some text we have given indicating what it is actually. So this is given at 2 comma some -10 comma 2 position, squares are given, and some 0 comma 2 position I think we have given stars, and at some position, what is that, 8 comma 4, we have given this diamonds. So location where we want to place the text, and that text we have to give it here. So this we call them as a annotations. And legend we have placed at the lower left corner, and the number of points we have placed is 1. Suppose if I give the number of points equivalent to 2, then 2 points in each one of that. like this. Now you see that you get 2 point. Where is this? Yeah, you see that now you got 2 points, right? Here 2 squares, 2 diamonds, 2 stars, like that you got, right? So that is indicating that number of points here. So if you give number of points equivalent to 1, see that now only 1 point, right? So I understood it, right? Annotation, y limit, x limit, xx, yx, and then group wise scattering. All these points clear? Not any responses today. I don't know what happened.
Yes, sir.
Sir, so can, once again, can we see the phone up? Um, So these checkings which we are plotting, no sir, y equal to 0, these are the values which are generated because of we would like to see the data set for this, for which this plotting has been done.
See, madam, we have generated 100 points.
Yes, random some values we give, no, n samples.
Let me open my whiteboard. Give me a second. I'll open. Where is my pen? Okay. Yeah, it is. Can you see my whiteboard?
Yes, sir.
Yeah. So now you have generated 100 points, right? Okay. So then indices are like 0, 1, 2, so on, 99. Okay. And this is a two-dimensional point and the corresponding label y. Okay. Y can be either 0, 1 or 2, as there are 3 groups. Okay. So the two-dimensional point and the corresponding label, two-dimensional point and the corresponding label, and so on. Okay. Right. So this is x you're saying, and this is y. Okay. So when you say this is x, okay, so how do you access this particular value in this x? X of 0, comma 0 and x of 0, comma 1. Am I right? This is the 0th dimension. This is the first dimension. 0, comma 0 is this. 0, comma 1 is this.
Yes.
Similarly, this is x of.
This we understood, sir.
This is 1, comma 0 and x of 1, comma 1, and so on. Right. So now when you're saying you're accessing x of y equivalent to 0. Okay. Y equivalent to 0, comma 0. That what it means is that wherever y is equivalent to 0, it means wherever y is equivalent to 0, those index numbers will be written here. Got it, madam? It means those indices you are accessing, like for example, let's say this is 0, this is 0, and this is 0. So
Yes.
it means what? It will generate x of 1, comma 0, x of what is this? 2, comma 0, x of 99, comma 0. Similarly for the other coordinate also.
Okay, sir.
Yeah. Got it, madam? Shall we move on?
Yes, sir.
Okay. So histograms. Histograms, you know, right? This kind of, right? There are different styles in this histogram type. You can set it. Okay. I forgot all the styles actually. I'm not remembering anything except for the bar. Okay. But there are various options for the histogram type. You can explore that. That's not an issue, of course. So here is the we're generating this data using the normal distribution np.random.normal, This location indicating that what is the mean value, and the scale is indicating what is the standard deviation value. So normal distribution is indicated with the two values, mean and the standard deviation. So location, which is the mean value, scale is the standard deviation value. Size is 500 points you want to generate. And similarly, this is location 6, scale is 2, size is 500. So the scale is more means the more spread will be there. If scale is less means more less spread will be there, and this is the mean value. So now we are creating histogram. We are creating a column stack of both X and Z because we just want to plot both of them at once. Number of bins that I want to create is 15. It means all these 500 points are binned into, are placed into 15 bins. Okay. Histogram type is bar. Like that, various options are also there. Skeleton type, like that, various options are there. And colors that we are giving here is the cyan and blue color. Cyan for the first one, which means it's for X. Blue is for the Z. Okay, and stacked equal to false. If you set this stacked equal to true, it will be like combining all of them, right? So now you see this, you will get this kind of plot. Okay, so this is like histogram. So if you set this stacked equal to true, then you see that now it is something like this. Okay, so this is a histogram. All right. The next one is the bar graph. This kind of figure, we often want this for comparison purpose, right? Fine. So to create this kind of figure, I'm generating X and Y coordinates. The different Y coordinates makes the different series, right? So X is same for all of this, not same, in fact, it is little bit here and there, but X is we have generated using the arrange function 5, okay, a range of 5, and Y1 is this, and Y2 is this, Y3 is this, and width of this bar graph is defined to be 0.2 that we are going to use in this width. Okay, so X coordinate is X minus 0.2 here, X here, and X plus 0.2 here, right? As we have defined the width to be 0.2, we have taken that, right? And Y1, Y2, and Y3 are giving same width, different colors we have given. Color is cyan here, color is orange here, color is green here. You will get this kind of plot. Okay, so these are the bar graphs. So there is another thing that we are taking here to show you that how to draw the horizontal bar graphs and the vertical bar graphs. So something like this. Okay, so this is, we call it as a horizontal bar graphs. This is a horizontal bar graph, and this is a vertical bar graph. And this is also defining the mean and the standard deviation of this error. Okay, so we'll see that. So for this purpose, I'm taking this iris data set. Do you have idea about the iris data set? Have you heard of it at least?
Yes,
Sir.
The
yes.
iris data set is about what?
Sepal length and petal.
Yes, sir.
This is about the
Flower.
flowers, right?
Yes,
How
sir.
many flowers? 3 flowers
Very
are there.
sona. Very
Yeah.
something like that. Very kona.
Great that you have idea about all this. Yeah, so iris setosa, if I remember correctly, there are iris setosa, iris versicolor, and iris virginica. 3 flavors. Yeah, 3 flavors, and each flavor is described with the 4 attributes: sepal length, sepal width, petal length, petal width. Okay, so this is the description about the data set. 4 attributes, 1 target value, and target value belong to one of the 3 classes, 3 flower types. Okay, so I'm loading this data set by calling this function, load iris function, iris data set. So if you want to get the feature values, call this iris.data. If you want to get the target values, call iris.data target. Iris is whatever the name that you give here. If you give data here, data set dot data set dot target, you can call whatever name that you give, call by that name. Iris dot data, if you get, you will get the attribute values. Iris dot target, if you call, you will get the target values. So here we are taking the mean and standard deviation to indicate that error. So mean plus or minus standard deviation we will give. The mean plus or minus standard deviation is given with that, indicated with this black color line in the figure. So the mean value is this, whatever that you see in the figure, mean value is this, plus or minus standard deviation is this line. Okay, So if the standard deviation is more, you will get a very lengthy line. If the standard deviation is less, then you will get a very small line. Okay. So you see this. All right. So we computed the standard deviation. We computed the average. We also computed this range. Okay. So now we taking the subplot. In the subplot, we are taking 1/2 grid, and this is at position 1. So this bar graph is the horizontal bar graph, this range of values, and also the average one we are plotting. Color I'm giving is the red color. Here X error is the standard deviation, which is indicated with that black color line, right? So alignment is center. This alpha indicating the transparency in the color. Suppose if I give more value, the transparency will be lesser. That we will see here. Okay, so something like that. But this is alpha indicating the transparency, right? So because I gave this 0.2, the transparency is more, right? Now white ticks, this is just a range underscore iris dot feature names. So feature names I'm giving as the white ticks. Okay. So now let me execute this. You see this, right? So these are the feature names: petal, sepal length, sepal width, petal length, petal width, right? So this we are getting it as a white ticks here. And similarly, I'm plotting the vertical bars also. So just call bar. If you want to plot the horizontal bars, call bar H. If you want to plot the vertical bars, just call bar. Same thing here also, alpha value is taken to be 0.3 here, x-ticks and the iris feature names. So here the rotation, another feature you can see, rotation equal to 45 degrees. So here, if you see this, the names are rotated slightly in the 45 degrees, right? So if you don't give rotation equal to 45 degrees, no, what happens? This looks very clumsy because of the names, they may overlap. Let me remove this and execute it. Now you see this. Okay, so they're overlapped. It's not so clear, right? So if it is something like this, you can rotate the axis and then give the appropriate rotation that is suitable based on the titles at the hand. Okay. And similarly, let me demonstrate this also. Suppose if I give alpha equal to 0.9 here, now you see that you've got the dark color, right? So transparency is less here, right? So suppose if I give 0.2 here, then the transparency is more. Now you see that very lighter color you have got there. All right, so that alpha indicates the transparency. So could you follow it? Shall we move on?
Yes, sir.
Yeah. The next one is the image visualization, that how to show the images, image kind of data set. So for this purpose, we are importing fetch Olivetti faces, which is the real-time data set. So I'm just getting that data set. Okay, I'm just plotting 6 of these images. So for k in the range of 6, subplot of 2, 3. So k plus 1 means it starts from 1 to 6. K is starting from 0 to 5. So k plus 1 means 1 to 6, right? So this is the function used to show the images, image show, right? So this is the data set of data of k. It means you're just fetching the data instance that is located at the kth position, and you're reshaping it to 64 by 64. Usually this is a feature vector. When you access a data set of data, this is a feature vector which is of size 64 times 64, right? All is like in one row, right? So now you have to reshape it like an image, right? Because you want to show that as an image, right? So 64 by 64, you're reshaping it. Color map is assigned as gray, right? And interpolation is nearest. This is something relevant to the computer vision. So now you see that like this, you're just giving the title as the target value. Okay, and then you just mentioned axis equal to off. If you don't mention the axis equal to off, no, you will get the axis also, the ticks also. Okay, we don't want that. That's why I said the axis equivalent to off. You see that you got the faces like this. So like this, you show any kind of images. Okay, so this is like handwritten digits. You see that. So these are the 8 by 8 images. You see that This is the image. It's not clear, but the data set is like that, 8 by 8 images. Okay, it's also the same here. So you're just what is that? Loading that data set and showing that data set, right? Digits dot image of that number, right? So like this, you can show any kind of images. You see that here you have the axis because we don't set the axis equal to off here. So this kind of axis you will get if you don't set the axis equal to off. Okay. Then we'll also see that graphical presentation using the pandas framework as well. Some selected graphical examples we'll see that it is useful for the visualization as well. So the same thing here also, the load iris data set we are taking. So you see that data frame pandas dot data frame of iris dot data. Okay, so the groups are list of iris dot target. Okay, so now you have the iris data frame that if you want to visualize the box plots of the different attributes, you know the box plots, right? Box plot is a 5-number summary of the data. Okay, so now you have 4 attributes: sepal length, sepal width, petal length, petal width. So each one of these attributes, you want to summarize them with the 5 numbers. What are the 5 numbers of the box plot? Minimum value in that column, maximum value in that column, median in that column, quarter 1 and quarter 3, right? So these are the 5 numbers: minimum, maximum, median, quarter 1 and quarter 3. So minimum is the minimum of all the values in that column, maximum is the maximum of all that values in the column, and median is the median of all those values in the column. What is quarter 1? Once you get the median, take left all the numbers left to the median. It means anything less than the median is the left of the median. Now take the median of the left half, that is the quarter 1. Median of the second half is the quarter 3, right? So now any data can be summarized using these 5 numbers, and here this top one indicates the maximum value, bottom line indicates the minimum value, green color one line indicates the median value, and this box indicates the distance between the quartile 1 to quartile 3, right? So that is how you can summarize each and everything using this 5-number summary, right? So box plot. So box plot, iris dot data frame of box plot. All right. So similarly, you can plot the density curves. I mean density distribution of these values. See, this is how these values are density. This is how, I mean, the density distribution of this different attribute values, right? Sepal length, sepal width, petal length, petal width. So only thing that changes is the kind. So here you want the density distribution. That's why the kind of plot you're selecting is density. Otherwise it's the same, data frame dot plot only. Kind of it will change. If you want to scatter, set the kind equal to scatter. If you want some what is that, curve kind of thing, then a different kind of. If you want a bar graph, set the kind equal to bar. So like that, kind will change. If you want hexagon, set the kind equal to hexagon. So this is all the distribution of these values. So according to that, now you see that kind is histogram. So plot kind equal to histogram. One particular feature, petal width you are plotting, kind equal to histogram. This alpha indicating the transparency of the color. Similarly, here kind equal to scatter. You see that scatter type. With different colors you set here. You see this. This kind is scatter. Petal length, petal width. How the points are distributed according to their petal length and the petal width. How the flowers are distributed according to the petal length and petal width. And different groups, different flowers are indicated with the different colors in this figure. Similarly, here the kind is hexagon. Hexagon means it is indicating the distribution of these flowers according to this sepal length, sepal width only. You see that this is indicating that how the points are distributed according to the sepal length and sepal width. You see that this is a indicator graph that you can see on the right side one. The darkest color means that there are 8 points in that position. So here there are 8 points. Here the distribution of 8 points are there at this sepal length and sepal width. Similarly, there are 8 points here. Similarly, there are other colors also indicating that how many points are present at that locality. So this is hexaband kind of distribution. Similarly, you have the scatter plots, scatter matrix, which is indicating that how the points are distributed according to the pairs of the attributes. So when you take the pairs of attributes and there are 4 attributes, then possible combinations are 4 by 4, right? So this would be like sepal length, sepal width, sepal length, sepal width, sepal length, sepal length, sepal length, petal width, sepal length, petal length, like that, all the possible combinations. And
Sir,
yes,
here this three colors are coming, but we are doing comparison between only two to know every time.
no,
Try to see.
two features you are selecting,
Yes,
but three
yes.
colors indicating the 3 kinds of flowers.
Yeah.
Yeah,
3 categories of the flower.
flowers, yes. And these diagonal values are indicated with the density distribution, that what is that you call KDE, right? Kernel density estimation or something like that, diagonal elements. Okay. So there is
Sir,
another
I have
thing.
one question.
Please.
Here we know that we have three separate kind of flowers, so we are giving different color schemes for each of the clusters. But what if the number of clusters is variable? Then how can I plot separate clusters in a separate color?
No, how come it is variable? You know it, right? The number of groups, whatever it is, either it is 10 or 11 or
Say
12.
depending on some condition, I am clustering
That
my
time
data set.
also, the condition, once you know that, right, you will be taking the, I mean, you can identify the number of unique values in that column. That gives you the number of groups. According to that number of groups, you can assign the number of colors.
If it is very large in number, then also I have to do it manually.
You can give it like one list and you can pass that list.
Okay, so the color value can be a number also.
Yes.
Okay.
Yes, that option, the links I have given to you, in that it is there.
Okay.
See, every color is a combination of the 3 numbers, right? Red color,
RGB.
quantity of it, yeah, RGB. So that through that fashion also you can give the color values.
Okay.
And there are some not only that, not only 3 color representation, there are other representations also, like the what they call it is what do you call the 16 bit representation? What is that? 10 is decimal, right? So 16, what do you call?
Hexadecimal.
Hexadecimal, sir.
Hexadecimal, right? Yeah. So that representation is also there. You can
Oh.
represent number through that representation as well.
Oh.
Yeah.
Thank you.
Yeah, the Seaborn library has, yes. Sir? Fine. Seaborn library, which is for some setting up the stylings and all. So here I said the Seaborn library sns.s. Now you see that the same plot. Now you have even the options of setting the styles also. I'm not demonstrating that here, but there are various other options in the Seaborn library if you want to explore. Now you see that same plot, whatever that we have plotted earlier. Now I am just plotting it again after setting this sns.set. Okay. Now you see that it is changing. Style is slightly different, right? So you can set the styles like this. snr.access style is white grid. Like this, various other options are there. I've just given few here. So with this white, so earlier it is like this without setting any styling and all. Now after setting the styling, now you see that white grid you have got. So like this, you can have, now you see that here also that same scatter plot, it is changing now, right? The style is completely changed. So you have an option to set the different kinds of styles here. Okay. Fine. So that's all about the data visualization. So see, if you look at the Python part that we have covered, I've just covered whatever is absolutely necessary for the programs that we're gonna discuss. Okay. So the aim is not to cover the whole Python course. Okay. So the portion that is required for us to understand this machine learning algorithms implementation, that part I have covered. I hope you understood that. Clear, right? So my intuition is that in covering this Python part. All right. So, but the main focus is on the machine learning only in this course, not on the Python, not on the mathematics, although we are covering those concepts. Okay. So am I clear? Shall we move on? So any queries? So shall we proceed to the next topic?
Yes, sir. Yes.
Yeah. So in this topic, we're going to cover some of the basic concepts of the probability. We'll start with very basics. So for those who know also, it's like a brush up of things. You can recollect the things. For those who don't know any of it is very much useful. Okay, so we'll start with the probability concepts. What is the probability? What is the random variable? And what are the different notions of the probability? Like we're going to see that joint, marginal, and conditional probabilities, the distributions. We will also see the discrete and continuous random variables and their distributions. We're going to see the expectation, variance, covariance, correlation, all these concepts also we're going to cover. And some of the example probability distributions also we're going to look at, right? So these are the things that we're going to cover, but it's not possible to cover all of them in another 1 hour. We left with only 1 hour time. So let us see to what extent that we can cover. I think today it's only possible to cover the basic concepts. Okay. So let us stop it in such a way that it gives some logical conclusion. So instead of starting at the random slide, so because of that, it may be little more or little less than 8 p.m. Right? So please be prepared for that. Okay. So what is, before we gonna see the probability concept, let us try to understand the difference between the probability and the statistics. So we all know the probability concept. Many of us familiar with this. At one point of time in our life, in our studies, we might have solved some probability related problems in which you might be asking a questions like, what is the probability that coin will land upon heads? What is the probability that dice will land upon six? Or what is the probability of picking a king from the deck of cards? Or what is the probability of picking a red color ball from the desk of balls? Or what is the probability of picking blue color socks from the drawer of the socks? These kind of questions you might have often heard of it, right? So if you look at all these questions that I have posed to you now, what is the probability? Probability is basically the chance of an outcome in the experiment or an event. We also call it as an event. So this experiment could be tossing a coin. This experiment could be rolling a dice. This experiment could be picking a card from the deck of the cards, or this experiment could be picking a ball from the drawer of the balls, right? So this experiment could be anything. So in all these things, we are interested in dealing with the prediction of the likelihood of the future events. So it means probability is dealing with predicting the likelihood of the future events. Underline this word future. So what is the probability that the coin will land upon heads? What is the probability that we will pick this red color card? Okay, so you're dealing with the likelihood of the future events. Whereas in case of statistics, it involves the analysis of the frequency of the past events. Analysis of the frequency of the past events. Like what are the COVID statistics in the last month? Or let's say that you have observed a sample of 1,000 people in a particular city and you have got the COVID positivity rate to be 60%. What is the COVID statistics of the whole population in that city, right? So basically, it involves the analysis of the frequency of the past events. In all these cases, you're trying to observe the sample and you're trying to infer the conclusions about the whole population based on the sample that you have observed. Okay, so is that fine? Are you with me? I know I'm going little slow. Yeah,
Yes,
but
yes.
I'm not giving any gap in between. That's why I'm a bit doubtful whether you could follow or not. Following, right? So
Yes,
my
sir.
intuition is to what is that? Utilize the maximum amount of time. At the same time, I want to ensure that you're following it. Okay, it's not that I'll be discussing something that you couldn't follow. Okay, so please let me know if something like that happens. Okay, so I can repeat that. So you'll see the example, then it will be more clear to you. So consider there is a drawer containing 100 socks. And we know the distribution of the socks. Let's say 30 of the 30 of them are red color socks, 20 of them are blue color socks, and 50 of them are black color socks. So this is the underlying distribution is known to us. Underlying model is known to us. We just want to see that what kind of data that we are likely to see given the underlying model. So like we can answer the questions like what is the probability that we draw two blue socks or two red socks from the drawer? Or what is the probability that we pull out three socks and in the three socks we get a matching pair? Or what is the probability that we draw five socks and all of them are black, right? So it means if you see, look at these questions, what is given to you? The underlying model or the underlying distribution is given to you, and you're asking questions like what kind of data you are likely to see given the underlying model. These are the kind of questions that we are expecting in the case of probability. But suppose if you have no clue about what is the type of socks present in the drawer, then you enter into the realm of statistics. So statistics help us to infer the properties about the population based on the random sample that we have observed. Like for example, let's take a random sample of 10 socks from the drawer. And we have observed that among these 10 socks, 1 blue color, 4 red color, 5 black color socks is there. So what is the total population of the black, blue or red color socks in the drawer? So you see that here, if you look at the probability concepts, there the underlying distribution or the underlying model is given to you. You're asking questions like what kind of data that you are likely to see given this underlying model. Whereas here, you're given with the data. You don't know what is the underlying model. You're given the data and you're asking questions like what kind of model might have generated this data. Okay, so it means you're observing the data and trying to infer what kind of model would have generated this data. Whereas in case of probability, you know the model and you're asking what kind of data that we are likely to see if this is the underlying model. That's the basic difference between the probability and the statistics. So in probability, we are given a model and asked what kind of data that we are likely to see. Okay, whereas in case of statistics, we are given data and asked what kind of model is likely to have generated this data. So I can give you one more example here. Let's say you have a fair coin. Fair coin means you know that equal probability of getting heads and tails. Okay, so now you will toss the coin for 100 times. Let's say that you got the probability I mean, you're asking questions like what is the probability of 60 or more heads, right? So you will get a single answer because of the standard computation strategy. This is the probability concept. You know the underlying model or the underlying distribution of this heads and tails, and you're you're expected to estimate the probability of a certain event. Okay, but if you have a coin of some unknown provenance, it means you don't know whether it is a fair coin or not. The task is to investigate that. Okay, so to investigate whether it is a fair coin or not, you toss the coin for 100 times and count the number of heads. So let's say you count 60 heads. When you toss the coin for 100 times, there are 60 heads. You got the 60 heads. So what are the possible conclusions that you can make out of this? One conclusion is that this is due to the random chance we have got this 60 heads. Okay. Another conclusion is that the coin is unbiased. The coin is biased coin. That's why we got 60 heads. Two conclusions are possible. Hello, agree? Two conclusions are possible, right?
Yes,
One
sir.
conclusion is that it is a biased coin. The other conclusion is that it is due to the random chance probability we've got this. So which one is correct? So your job is as a statistician is to draw conclusions from this data or inferences from this data based on some assumptions about the data. All right. So that's the basic difference between the probability and the statistics. Okay. So in this lecture, we'll be mainly focusing on the probability concepts only, not the statistics concept. So statistics also, if you have to cover, we need at least one or two more sessions. That is not possible for us. Okay. Anyhow, that I mean, it is easy for you to explore the statistics.
So statistic is not possible today. Tomorrow.
Not possible. That is, I mean, you have to get into another view of it. Okay.
Another
So it's
course.
not that, no, another course, no. It doesn't require another course. I mean, to just get the idea about it, you didn't require another course. If you have to get the whole thing about that, then of course, another 10 days is required. But anyhow, to just get that view, you may require some 2 sessions. Okay. That hypothesis testing, statistics aspect of that, all that we may require 2 classes. Anyhow, yeah, but the theme of our FDP, I mean, so that course is slightly different, so we'll not get into that. Okay, but as and when it is required, I'll definitely try to cover some part of it. Okay. Yeah, so let us discuss about the probability concept. So the probability is often associated with some event, at least one event. Event could be rolling a dice, event could be pulling a color ball, event could be picking a card, event could be anything. In all these examples, outcome of the event is random. In a sense that, for example, if you toss a coin, you don't know whether the coin will land up on head or tail. It's random. If you throw a die, you don't know whether it will land up on 1 or 2 or 3 or 4 or 5 or 6. It's again random, right? So if you use some variable to indicate the outcome of this event, that variable we call this as a random variable, because the outcome is random and the variable representing this random outcome, we call that as a random variable. So the random variable is a variable that assumes numerical values associated with the random outcome of an experiment. Okay, so we don't know what outcome you would get, right? So informally, a random variable x denotes the possible outcome of an event. So this outcome, it can be either discrete or it can be continuous value. So the random variable can be a discrete random variable or it can be continuous random variable. So what is the difference? You already understood this difference in the introductory part. What do you mean by the discrete random variable and what do we mean by the continuous random variable?
Oh,
In continuous variable, there is a range of values.
It can take any value, in fact, right? So it can't restrict
yes.
them to be certain set of values.
Restrict certain limitations of
So in discrete, we
Limited.
have got some
limit
finite and countable number of
finite.
values.
Yes.
And if you take any 2 continuous values, you cannot get any other value which is in between them, right? So the discrete random variable is, if you pick up any 2 consecutive outcomes, I can't get any other value which is in between. Like for example, when you throw a dice, right? It can be either 1 or 2 or 3 or 4 or 5 or 6. The outcome can be any one of the 6. But it's not possible to get 1.5, 2.3, 4.67, something like that, right? So in mathematics, we would say that list of outcome is countable. Here are the few examples of this. Experiment, let's say experiment is making 100 sales calls and the random variable indicating the number of sales. So when you make the 100 sales calls, number of successful sales could be 0, could be 1, could be 2, it could be 100 as well. but it is some number only. It's not 1.2 cell, 3.6 cell, right? So these are the possible values. Similarly, when you inspect 70 radios, number of defective can be 0 or 1 or 2 or so on 70. Similarly, when you conduct an experiment of answering 33 questions and the random variable indicating the number of correct ones, the possible values are any integer number between 0 to 33. All right. Similarly, the continuous random variable, on the other hand, the continuous random variable can take any value. Let the experiment is weighing 100 people and the random variable indicating the average weight. This could be any number, right? It could be 45.1, it could be 78.2, it could be 90.12, it can be 80.45. So it can take any value. You can't restrict them to be certain values. So similarly, height, time, amount spent, all these are the examples of the continuous random variable. Okay. So in the probability, we are often interested in knowing the probability of this random variable taking a certain value. Like for example, what is the probability that coin will land upon heads? So you are interested in taking the coin taking a certain value, heads or tails, or what is the probability that die will land upon tree? So you are interested in knowing that what is this random variable, probability of random variable taking a value 3. Or what is the probability that I pick a king or a red color card? It means you're interested in knowing the random variable taking a red color, right? So like this, you're interested in knowing the probability of this random variable taking a certain value. Like, oh, for what is the probability that average marks less than or equal to 70? Or what is the probability that height greater than 5.5? So something, these kind of questions that we ask, probability of random variable taking a certain value. Okay, so there are different types of probability. Probability can be either marginal, joint, or conditional probability. So these notations you already know. At lots of places you might have already gone through them. Even in the case in Inter also we get this probability concept. Okay, so suppose they ask you what is the probability of picking a red color card from the deck of cards. What is your answer?
Oh,
How many total number of cards?
26 by 52.
Total number of cards are 52, and out of them 26 are red color. So this is 0.5. So this is the marginal probability. It's because you're just interested in probability of a certain event, irrespective of the other events. So you're not caring whether the card is a red color, whether the card is a king, queen, or whether it is a heart symbol or a diamond symbol. You're not caring about any other aspect of it. You're just interested in knowing the probability of the red card. So that's the marginal probability. The joint probability is the intersection of the two or more events. Like for example, if I ask you a question, what is the probability of picking a red color king card? Okay, it means it should be red as well as king. Okay, the two things. Okay, so if you look at the space of red color cards, how many red color cards are there? 26 are there. If you look at the space of only kings, how many kings are there? 4 kings are there. So you look for the intersection of both red color and king cards. So how many red color king cards are there? Only
2.
2, right? So only two red color king cards. So the total number is 52 and red color king cards is 2. So 2 by 52, this is 1 by 26. This is the joint probability, which is the intersection of two or more events, right? So another one is the conditional probability, which is the probability of one event given that other event has already happened. Like for example, suppose if I give you information that it is the red color card, I ask a question, what is the probability that it is a king? I've already given you information that it is a red color card. I'm asking a question, what is the probability that it is a king? So how many red color cards are there?
2 by 26.
26 red color cards are there. Out of them, there are 2 kings. So we are just exploring the space where this condition matches. So we are not exploring the whole space. We are only exploring the space where this condition is satisfied. red color card. So the 26 cards with the red color. So therefore, we are just taking the space in the denominator, right? Size of that space in the denominator. All right. So, so let us first try to understand these notions with the discrete case. Then we will extend it to the continuous case. Okay. So in this experiment, there are two events. One is tossing a coin, another one is throwing a dice. This is the second event. And this is the probability distribution of these two events, joint probability distribution. So you see that this is the probability of die equivalent to 1 and coin equal to heads. And similarly, this is the probability of die equivalent to 3 and coin equal to tails. Okay, these are the joint probabilities, the intersection of two events. Okay. Now, suppose if I ask you for the marginal probability, what is the probability of heads? So when I ask what is the probability of heads, it means what? Irrespective of whether the die equal to 1 or die equal to 2 or die equal to 3, it doesn't matter to me. I'm just interested in finding what is the probability of heads, isn't it? So I have to take sum over all the possible values for the other value, other event, die equivalent to 1, die equivalent to 2, die equivalent to 3, die equivalent to 4, 5, 6, right? So when you take sum over all these values, you get the marginal probability of heads, so which is equivalent to 1 by 2. Similarly, suppose if I ask you what is the probability of die equivalent to 5, what is your answer? Die equivalent to 5 means you are not interested in whether the coin equal to heads or coin equal to tails, right? So you're just interested in the probability of die equivalent to 5. So you just take the sum over all the other, sum over the probabilities with respect to the other random variable. So 1 by 12 plus 1 by 12, which is 1 by 6. This is also the marginal probability. Okay. So if you take the probability of heads equivalent to probability of heads comma die equivalent to 1, die equivalent to 2, and so on, die equivalent to 6, which is equivalent to 1 by 2. Okay. So this we call it as the sum rule. Okay. This we call it as a sum rule. So sum rule means if you have taken probability of x, so take sum over y, probability of x comma y. So for different values of y, you're taking the joint probability and taking sum over that. Similarly, if you take the probability of y, this is the sum over x, probability of x comma y. So these two we call them as the sum rules. Sum rules. Okay. So is that clear? Are you with me so far? Following the probability concepts?
Yes, sir.
Yeah. Thank you. So the next one is conditional probability. So what is the conditional probability? Probability of one event given that already another event has happened, right? So in the case of conditional probability, it is important to distinguish between the dependent events and the independent events, because the intuition is different in both the different in both the cases. Okay. So conditional probability refers to the probability of an event given that another event has already occurred. So first, it is important to distinguish between dependent and the independent events, because the intuition is a bit different in both the cases. So what do we mean by the dependent events and what do we mean by independent events? So let us understand these two concepts through examples. So independent event example is the dice and the coin that we have seen in the previous slide. So why they are independent events? These two events are independent of one another because output of one event is not influencing the outcome of another event. Outcome of one event is not influencing the outcome of another event. Then we call them as the independent events. So let us take the dice and coin example. Suppose I throw a dice.
Excuse me, sir. Can we tell that events are mutually exclusive?
Independent events?
Because when one is happening, the other won't happen.
It's not like that. So try to understand. I hope you will get through this example. Otherwise, we'll discuss it. Okay. So let us take a coin. Coin example. Suppose I throw a coin. I've got the outcome as a head. Okay. Now I ask you a question of what is the probability of die equivalent to 1 given that coin equal to heads. What is your answer? It's a fair die, it's a fair coin. What is the probability of die equivalent to 1? It's a 6-face die. What is the probability of die equivalent to 1?
1 by 2.
6-face die. It is a 6-face die.
1 by 6, sir.
1 by 6, right? The 6 possibilities, getting 1 possibility is 1 by 6, right? Now I gave you an information that, let's say I have tossed a coin. I've got the coin outcome as a tail. Now again I'm asking a question, what is the probability of die equivalent to 1 given that coin equal to tails?
1 by 6.
1 by 6. Is it changing?
No.
Whatever is the outcome of the coin is not influencing the outcome of the die. Am I right? Right. So then we call them as independent events. Is that clear, madam? Now?
Yes, sir. Absolutely.
Yeah. So now let us talk about the dependent events. Dependent events, let's say that 2 events picking up a card consecutively 2 times. Okay. First time when you pick the card, that is event 1. Second time you pick the card, that is event 2. Let's the random variable associated with event 1 is x. Random variable associated with event 2 is y. Okay, so now I ask a question. I said that x equivalent to king. I mean, when you pick a card for the first time, you got king, x equivalent to king. Now I'm asking a question. What is the probability of y equivalent to some queen, given that x equivalent to king? What is the answer? Without replacing the first one. You're picking the second card without replacing the first one and asking a question, what is the probability of getting queen when you pick the card for the second time, given that the first card is king? Once the card is picked, how many cards are left?
5.
Huh?
51.
51, right? Total 52 only, not
Acha,
50. Yeah, 51. You're left with 51 cards. Out of that, how many queens are there?
4.
Out of 4 are there because the card picked is the king, not queen, right? So 4 by 51.
Yeah.
Okay. Suppose now I ask a question. What is the probability of y equivalent to king given that x equivalent to king?
3 by 51.
3 by 51.
51.
3 by 51. It means what? Outcome of one event influencing the other one or not?
Yes.
Right. So then we call them as the dependent events. Okay. So if the outcome of one event influencing the outcome of the other event, then we call it as a we call them as a dependent events. If the outcome of one event is not influencing the outcome of the other event, then we call them as the independent events. And for the independent events, probability of x given y is equivalent to probability of x, right? If x and y are independent of one another. That's why you might have seen this, right? If the two events are independent of one another, what is the joint probability? Probability of x comma y?
P of x.
P of x times P of y, right? If they are independent of one another, joint probability equivalent to product over the individual probabilities. Why is this? Because there is some convenient relationship between the joint probability and the conditional probability. The relation is like this. Probability of x comma y is equivalent to probability of the first event times the probability
You're
of the
something
second.
little bit.
Okay, is it for only him or everybody else?
Only him.
Okay, sir, please check your internet connection. Maybe problem with that or your audio connection. Yeah.
in between.
Yeah, so for others it is fine. I mean, it means problem is not from.
Sometimes it is false.
So sometimes it is creating problem for you also. Can few more people? Yeah, everybody it is like that. Sometimes it is a problematic.
What? So actually,
Yes, sir.
there was
Yes,
a
sir.
My
problem
voice, is it
Sometimes.
clearly audible?
Yes, sir.
Right now you are audible, sir.
Yes, yes, clearly audible, sir.
Not right now, like throughout from the beginning.
So
Was there any
sometime
from
your
the
problem?
voice is
beginning is
missing.
fine, sir.
Yes, sir.
Okay.
Fine, sir. Fine,
In the
sir.
beginning it was fine, sir. Right now little bit in between it is missing little bit.
Yes, sir. In between sometimes.
Okay. I mean, if it is not manageable, please let me know. I will exit and join. Okay.
Fine, sir.
Yeah. So Syed replied saying that for him it is fine all the time. It may be due to the internet connection from your side also. Maybe sometimes signal is dropping. Okay.
Okay, sir.
Yeah, probability of x comma y is which is the joint probability is equivalent to probability of the first event times the probability of the second event given the first event. Okay. So if the x and y are independent of one another, what is the probability of y given x? If x and y are independent of one another, it is equivalent to probability of y only, right? Right. That's why this is equivalent to probability of x times probability of y when they are independent of one another. Got it, right? I hope this is clear. Shall we move on? Or should I repeat?
Sir, repeat no, sir, please.
Yeah, sure. Sure.
Last three questions.
Yeah. You know, ma'am, there is some relation between the conditional probability and the joint probability. You know, this joint
Yes,
conditional
yes.
probability x given y is equivalent to probability of x comma y divided by probability of y. Isn't it? That's what we have
Yes.
seen. When you
Yes,
say that
yes.
what is the probability of what was the question that we have answered? Red
Getting
color
the
x equal, oh sorry, what is the probability
the
of king
king
given
and
red?
queen, sir.
Yeah, no. Probability of king given
Right.
red color.
Action.
So this is equivalent to what? Probability of
20.
king and red
52.
divided by
2 by
probability of
26.
Red.
probability of red.
2 by 26.
So this is king and red probability is how much? This is 2 by 50,
26.
52, right?
Sir,
26.
26, no, sir, getting probability of red.
No. Joint probability. I'm asking about the joint probability. King and red, joint probability. And divided by probability of red is how much? 26 by 52. So this 52 and this 52 get cancelled and we got 2 by 26, isn't it? Which is the probability of king given red. I'm just giving example for this, madam. Relationship between the joint probability and the, relationship between the conditional probability and the joint probability. So the conditional probability of x given y is equivalent to joint probability of x comma y divided by probability of y. Am I right, madam?
Yes, sir.
Yeah. So now there is more convenient way of looking at this. Okay, if I bring this y this side, how can I write this? Probability of x comma y is equivalent to probability of y times probability of x given y. Can I write this? Hello, madam?
Says true, sir.
Huh?
Yes, sir, we can write.
I can write this, right? Or in other words, I can also write this way. Let me erase all of this. Let me write. Please let me know if you're not following it. Okay. Because if you miss one thing, it is like a chain. You will miss further things also. So if I write probability of y given x, can you tell me what is the probability of y given x using the same rule? Probability of x given y divided by probability of x. Am I right? Equivalently.
Yes, sir.
Right. So now I can write this probability of x comma y is equivalent to probability of x times probability of y given x. Am I right? If I bring this probability of y this side, then this is equivalent to probability of x times probability of y given x. Can I write this?
Yes, sir.
So how do we interpret this? This is joint probability is equivalent to probability of the first event times probability of the second event given the first event. The joint probability is equivalent to probability of the first event times probability of the second event given the first event. Okay, so that is what is the joint probability. All right, so now I said that if the events are independent of one another, probability of y given x is just probability of y because it is just independent of x, right? Whatever is the x value, this is just probability of y only. Am I right? So what is the probability of coin equal to head given it is die equivalent to 1? It is 1 by 2 only, right? So what is the probability of coin equal to tail given die equivalent to 2? This is 1 by 2 only, irrespective of whatever that it is the die value, it is just 1 by 2 only, right? So probability of coin equal to head given die equivalent to 1 is probability of coin equal to head. Agree? When the events are independent of one another.
Yes, sir.
So can I write this probability of y given x equivalent to probability of y when the events are independent of one another?
Yes, sir.
Right. So if they're independent of one another, how can I write this equation? Probability of x times probability of y. Am I right? So the joint probability is the product of the individual probabilities when the events are independent of one another. Got that point, madam? Clear? Now
Yes,
can
sir.
you tell me what is the joint probability of x, y, z if I say x, y, z are independent of one another?
Into probability of y into probability of z.
Product of their individual probabilities.
Probability of x times probability of y times probability of z. Yeah, so please remember this point because this we're going to use it at multiple places as we proceed. Okay, this is one point. Tell me the other point. I have one question for you. Let me arrange all this. Now you have got probability of x comma y, probability of y comma x. Let's say x comma y comma x. Are they different or the same? Joint probability of x comma y and y comma x. Are they different or the same?
They are different, no, sir.
They
Different.
are not dependent, then it will be the same.
Yes.
What is the joint probability?
Joint probability is the
Intersection of two or more events, right?
yes.
Right. So x in x comma y, and I say it is probably x intersection y. When I say y comma x, it is y intersection x. Are the same or different?
Same.
Same only, right? Okay, whether dependent or independent doesn't matter in the joint probability. In the conditional probability, it does matter. Okay. So now, yeah, they're same. Probability of x given y is equivalent to probability of y given x, right? So if I expand them, probability of y comma x is probability of y times probability of x given y. And I expand probability of x comma y, this is equivalent to probability of x times probability of y given x. Are the same? Can I equate them? Probability of y
Yes,
equivalent
sir.
to probability of y times probability of x given y is equivalent to
Probability of
probability
x.
x times probability of y given x. Okay, so from this, can you tell me what is the probability of y given x?
Probability of y divided
y given x. Y given x is this. I can bring this other side, right? What happens if I bring it to other side? This is probability of
Why?
x given y times probability of y divided by probability of
Probability of X.
x. Probability of y given x equivalent to probability of x given y times probability of y divided by probability of x. We call this as a Bayesian theorem. Bayesian theorem, which forms basis for many of the algorithms like naive Bayes classifier, maximum a posteriori classifier, maximum likelihood classifier, naive Bayes classifier, Bayes optimal classifier, Bayesian belief networks. All these are based on this theorem. Probability of y given x equivalent to probability of x given y times probability of y divided by probability of x. Okay. So is that clear? Shall we move on?
Yes, sir.
Yeah. So let us just again go through all these things quickly. So notation that we use for the joint probability is probability of y given x. Pipe symbol we use. And mathematically, there is a convenient relationship between conditional probability and the joint probability. Because probability of y given x is equivalent to probability of y comma x divided by probability of x. And it is more convenient to look at it in another direction. That means joint probability is, if you bring this other side, joint probability is equivalent to probability of x times probability of y given x. And so to calculate the probability that both event occurs, we have to take the probability of the first event times the probability of the second event given the first event. And we know that probability of x comma y is equivalent to probability of y comma x, joint probability. So if you expand them, you will get this. If you bring this probability of y the other side, probability of x given y is equivalent to probability of y given x times probability of x divided by probability of y, which we call it as the Bayesian theorem. Okay, is Bayesian theorem clear to all of you? Yeah, this dependent independent events we have already discussed. I am skipping that. Now another one, probability distribution. What is probability distribution? How the probability values are distributed according to the output values, right? That's what is the probability distribution. The probability distribution is the list of all the possible outcomes of a random variable along with their corresponding probability values. Here, if you take a fair die, probability distribution of the different values is 1 by 6, 1 by 6, and so on 1 by 6. So this is an example of the discrete univariate probability distribution with a finite support. Okay, so try to understand each one of these terms in this. What do we mean by discrete? Why is it discrete probability distribution? Because
We
the
have 6
outcome is
options.
discrete.
Yes.
Yeah, because the outcome is discrete. Why is it univariate? Univariate because it is only talking about one event, not the multiple events, right? Only one event, outcome of the die, right? That is why it is univariate. Finite support because there are finite and countable number of values here, right? So there are some axioms need to be satisfied by the discrete random variable. So we use the P of x to denote the probability of x equivalent to x. Here, P of x, we call it as the probability mass function. So probability values, what is the range of the probability values? Can you tell me? To 1? 0 to 1. It means it should be greater than or equal to 0. Any probability value must be greater than or equal to 0 or less than or equal to 1. Right? So this is the first condition. And if you take the sum over all the probability values, probability distributions, this should be equivalent to 1. Like for example here, if you take sum over all the probability distributions, this should be equivalent to 1. That is the another condition. Sum over P of x must be equivalent to 1. So this is the discrete case. So we'll see another example of the discrete probability distribution. So here is an example of tossing two coins and the random variable indicating the number of tiles. Okay, random variable indicating the number of tiles. So what are the possible values for the random variable? If the random variable indicating the number of tiles, number of tiles can be 0, it can be 1, it can be 2. 3 possibilities, right? And you toss 2 coins and the random variable indicating the number of tiles. What are the possible values for this random variable? Number of tiles could be 0, or it could be 1, or it could be 2. 3 possibilities only, right? Hello? Am I right?
Yes, sir. Yes, sir.
Yes. So what is the probability of number of tiles equivalent to 0? If you toss 2 coins, what are the possible possibilities if you toss 2 coins? Either both of them can be heads, one head, one tail, or both of them can be tails. These are the 4 possibilities only, right? So in how many of these 4 cases the number of tails equivalent to 0?
1.
Only one case, right? So there are 4 possibilities. Out of them, in only one of the case, number of tails equivalent to 0. So the probability of number of tails equivalent to 0 is 1 by 4, which is 0.25. And what is the probability of number of tails equivalent to 1? How many cases are there?
2 cases.
2 cases are there. These 2 are the cases. So 2 by 4 is the probability of number of tails equivalent to 1. And probability of number of tails equivalent to 2 is 1 by 4, because there is only one case with number of tails equivalent to 1 out of 4 cases, right? So this is how the probability values are distributed according to the number of tails. This is the probability distribution of the probability values are distributed according to the number of tails. Probability distribution according to the number of tails. Okay. So there are multiple ways that you can present this probability distribution. Let us see what are those ways. So one possibility is listing out each possible outcome and the corresponding probability value. So number of tails 0, the corresponding probability is 0.25. Number of tails 1, the corresponding probability distribution is 0.5. Number of tails 2, the corresponding probability distribution is 0.25. This is one possibility to visualize this. Another possibility is like a table. Number of tails t is 0 and the corresponding probability 0.25. Number of tails 1, the corresponding probability is 0.5. 2 and the corresponding probability is 0.25. The most familiar one, all of us know about this. The next one is the graph, right? This kind of distribution you might have seen in the grades also, right? So these are the possible values and these are the corresponding probability distributions. Okay. There is another important way that you can visualize this, that is through the formula as well. Formula. You can summarize this through the formula also. Like you can represent this with this formula. Like for example, if I want to know what is the probability that number of tiles equivalent to 1, then what is the probability of x equivalent to 1? So how many values are there? How many n values are there? What is the value of n? How many coins are tossed? 2 coins are tossed, n equivalent to 2. So 2 factorial divided by 1 factorial, x is 1, right? Times 2 minus 1, which is 1 factorial, times probability of heads, which is 0.5 to the power, x value is 1. Probability of tails, 1 minus p, which is 0.5 to the power n minus x, which is 2 minus 1, that is equivalent to 1. So what is this? 2 times 0.5 times 0.5, which is equivalent to 0.5. Am I right? Hello?
Yes.
Lost. Are you following? I'm sorry about that. But
Absolutely, sir. Nice. Always.
yeah. So 0.5 is this. This is another way that you can express this probability distributions, which is important, especially when you're dealing with this continuous cases. Okay. So yeah, so let us proceed. So the continuous probability distribution. So far we have seen discrete probability distribution. That is very easy for us to visualize, discrete probability distribution. But continuous probability distribution, sometimes it is a bit confusing for us. So, but then I'll try to explain so that you will understand it. Okay. So yeah, here, if you take the continuous probability distribution, it is meaningless to ask that probability of X taking a certain value. Let me put it this way. Suppose if I ask you a question, what is the probability that average marks, what is the probability that average marks is equivalent to, 65.613528. Does it make any sense to you? What is the probability that average marks of a class is equivalent to some 65.613528? Does it make any sense? Most of the times it is 0. Am I right? Hello?
Yes, sir.
Because average marks cannot be exactly equivalent to 65.61 to 613528, right?
Yes.
If I ask a question like, what is the probability that average marks less than or equal to 65, it does make some sense. Or what is the probability that average marks are in between 60 to 70, it does make some sense. But if I ask a question, what is the probability that average marks is equivalent to 65.123456, does it make any sense? Doesn't make any sense, and most of the times it is 0. Right? It's meaningless and 0 most of the times. So instead, in case of continuous probability distributions, we try to pose questions like, what is the probability that this random variable taking the values between certain range? So what is the probability that this random variable is in between A to B? So these are the kind of questions that we pose. So here, if you visualize this query, if you visualize this probability distribution here, then when you are just posing, or if you are interested in knowing the random variable taking certain range of values A to B, it means you are interested in knowing the area under curve highlighted with this gray color region in this figure, right? So the total area under curve is equivalent to 1 because the total probability is equivalent to 1. Sum over all the probabilities must be equivalent to 1. So the total area under curve is equivalent to 1. Okay. So when you ask a question that probability of this random variable taking certain range of values, you are asking for some portion of this area under curve, which is highlighted with this gray color region in the figure. So this is often expressed with this integral over a to b f of x dx, where f of x is the probability density function indicating how these values are distributed, right? Density distribution of this x values. So don't worry about it. If you couldn't follow it completely, we'll see the example, then you will understand it better. Okay, but you got some idea at least, right?
Yes, sir.
Yeah. So let us take an example. There is a company which is producing the metal cylinders. Okay. And the random variable indicating the diameter of the metal cylinder. Random variable indicating the diameter of the metal cylinder. Right. Because the diameter value can be anywhere between 49.5 to 50.5. It is an example of the continuous random variable. The diameter of the metal cylinder produced by this company can be anywhere between 49.5 to 50.5. So because it can be anywhere in between 49 to 50.5, this is an example of the continuous probability distribution, continuous random variable. Okay, convinced, right, that it is a continuous random variable? Hello?
Yes, sir.
Yeah.
Yes.
So similar to the properties of the probability mass function in case of discrete probability distribution, here also we have some rules. So f of x must be greater than or equal to 0, which is the probability density function in the continuous case. There it was sum over p of x must be equivalent to 1. Here it is integral over x f of x ds must be equivalent to 1. This is because it's a continuous case. And here is the diameter of the metal cylinder having this probability density function. Okay, so this is the function or a formula which is giving you the density distribution of these metal cylinders. It means how these metal cylinders are distributed according to their diameter, right? That's what the information this probability density function is giving you. How the metal cylinders are distributed according to their diameter values, right? So here we have the probability density function, the distribution is indicated with this formula. If x is in between 49.5 to 50.5, anywhere else it is 0. This means that there is no metal cylinder with a diameter less than 49.5 or greater than 50.5. Okay, anywhere else the distribution is like this, which is indicated graphically like this. So you can see that distribution is like this. Most of the metal cylinders are around 50 diameter. Very few are at 50.5, very few are at 49.5. So the distribution is something like this. Most of them are at 50. As you go this side or this side, distribution is reducing gradually. Okay, so I hope you understood the distribution of the metal cylinders, graphical part. Clear?
Sir.
Yes. Okay. So now, whether this is a valid probability density function or not. So to see that, we have to check the integral over x, f of x dx must be equivalent to 1. Okay. So we know what is f of x. This is f of x. Okay. And possible values for x possibilities are 49.5 to 50.5. F of x dx. Okay. And this is f of x, right? So let us say after solving this, I've got some function which I indicated with capital F of x. This should be in the range of 49.5 to 50.5. So let us generalize it. Let us say in the range of a to b. How do you solve this? We take f of b minus f of a. Am I right? Hello? Do you know how to solve the integrals, right? Integral is
Yes, sir.
Yes.
position of the derivative. If you take the derivative of this, you should get this. Okay.
Yes, sir.
So now you got 50.5 is a b value, 49.5 as a value. Substituted them. 50.5 substituted. This is f of b. 49.5 substituted. This is f of a. So I've got 75.5 minus 74.5, which is 1. It means the total area under curve is 1. Therefore, it is a valid probability density function. Okay. So now a question to you, right? Suppose I ask you a question. What is the probability that metal cylinder diameter is in between 49.8 to 50.1? How do you do that?
Then the x value changes to 49.8 to 50.1.
It means instead of 49.5, we'll be taking 49.8. Instead of 50.5, we'll be taking 50.1. Am I right? So substitute and you will get some value here. That is the area under curve, which is in between 49.8 to 50.1, right? So something like this, highlighted with a blue color in this figure, right? So 49.8 to 50.1, which is 0.432. The next one is what's the time? And the 10 minutes. Okay. Okay. Yeah. So another one is the cumulative distribution function. So cumulative distribution function is indicated with capital F of x, which is indication of probability of x less than or equal to x. It means with some variable x, we'll be computing the probability of x. It means the upper range will not fix it to certain value. We'll keep this as a variable as it is. Lower bound we know 49.5. So integral over 49.5 to x. You solve the problem, you will get the cumulative distribution function. So 49.5 to x. To avoid confusion, we have changed the variable to y here. Right. Solve for this. This is the cumulative distribution function. A question to you now. Suppose if f of x is given to you, capital F of x, which is an indication of probability of x less than or equal to x. Okay. And given this cumulative distribution function, can you answer this question? What is the probability of x less than or x is in between 49.8 to 50.1? How do you solve this using the cumulative distribution function?
So the lower limit will be 49.5.
49.8. Okay. But Naini, I'm asking you a different question. I'm not asking to solve through this previous procedure. Given this cumulative distribution function, how can you make use of the cumulative distribution function to answer to this query? And cumulative distribution function says probability of x less than or equal to x. So it means f of 50 means this is equivalent to probability of x less than or equal to 50. Okay, so f of 50.1 means p of x less than or equal to 50.1, like this. So using this, can you answer for this question? What is the probability of x is in between 49.8 to 50.1? So this is the area, total area under curve is 1. Let's say this is 49.8, this is 50.1. Okay, so if x less than or equal to 50.1, f of 50.1, what is the area that it is giving? Probability of x less than or equal to 50.1. Isn't it this area? Hello? Isn't it this area?
Yes, sir.
Yes.
Suppose if I compute f of 49.8, what it is computing? Probability of x less than or equal to 49.8. Isn't it this area?
Yes, sir.
Yes.
But what I am interested in? I am interested in this area.
In
How do you
between.
get that?
Subtract
Subtract. What do you subtract? F of 50.1 minus
Yes.
f of 49.8, isn't it? So that's what we are doing. Okay. Clear, right? How to use the cumulative distribution function to answer the range queries. So it is visualized like this. Cumulative distribution function is a monotonically increasing function. So x less than or equal to 50 is this, okay, and 49.7 is this. This is the difference, which is that 0.396. All right. So we understood the different notions through the discrete probability distribution. Like what is the marginal probability, what is the joint probability, all that we understood, right, through this discrete variables. But what does it mean in the case of continuous probability distribution is the question. Okay. So what is the sum rule or the joint probability, marginal probability in the case of discrete random variables? Probability of x is sum over y, probability of x comma y. And probability of y is sum over x, probability of x comma y, right? So this we called it as a marginal probability or sum rules. Hello, do you remember this? This is for the
So 1 by 2 we got no, sir. Adding
yeah. So this is for the continuous case, right? Sorry, discrete case. What it is for the continuous case? So here we have a sum over, here we have an integral over. Probability of x integral over probability of x comma y equivalent to y dy. Similarly here probability of y is integral over x, probability of x equivalent to x comma y. So what is that it means? Okay, you just changed sum to integral because it's a continuous case, but we have to understand it, what is the intuition behind it? What is that it means? Okay, so let us visualize this here. So this is the distribution. Let us call this as a x, let us call this as a y. This is how these x and y values are distributed, right? The density distribution of x and y values. So you can imagine the distribution is more here, right? Right. So if you can imagine it like a hill in the three-dimensional space. Okay, I mean the distribution of x and y values. Many values are here, few values are here, here, like that. Okay, you can imagine that like a hill in the three-dimensional space. Distribution. Got it, right? Hello, are you with me?
Yes,
Yeah.
sir.
So now when I'm asking for what is the probability of x? Give me a second, I'll have some water. When you're asking for probability of x, it means you're asking for how the x values are distributed. It means irrespective of y values, how the x values are distributed. What is the distribution of the x values? That's what you're asking. So irrespective of the values that the y is taking, how x values are distributed. If you see only look at x values, how x values are distributed? You see that most of the points are here, right? As we go this side or that side, it is slightly reducing. As you observe, the distribution is slightly reducing. Agree? It is something like this. Am I right? So it is something like this. It is something like this. Okay. It means this is how the x values are distributed irrespective of the y values. That's what it means. So this is giving you the probability distribution of the x values irrespective of the y values. That's what the marginal probability distribution in case of continuous case. Similarly, when you ask for the probability of y, how y values are distributed irrespective of the x values. So this is how the x values are distributed y values are distributed irrespective of the values that the y is taking. So this is how they are distributed. So got it right? The interpretation of probability of x and probability of y. Clear? Shall we move on? I think
Yes,
couple
sir.
of you
Yes,
are
sir. Yes, sir.
exhausted.
No, no, sir. Not
No.
exhausted. No.
Yeah. Yeah. Thank you. Thank you. All right. Then the next one is the conditional probability. We have seen some examples also with respect to the discrete case. And what is the probability of king given red? This is 2 by 26. Right. What is this 26? The space where this condition matches, right? Right. And if you are not speaking anything, please mute yourself. It is creating some noise. Okay, so this is like you're just exploring the space where this condition matches, right? Okay. Similarly, the discrete case, you see this. When you ask a question, what is the probability of x given y equivalent to y? It means you're just looking for the row where this condition matches. Within that row, what is the probability of x you're estimating? Similarly, when you ask a question, what is the probability of y given x equivalent to x? Just looking for the column where this condition matches, and then you're just exploring that space, estimating the probability of y within that column, right? Isn't it? So what it means for the continuous case. So let us take some example of this image, and this each row indicates how the pixels are distributed according to their intensity values, pixel intensity values. So let us take y equivalent to y1. There are different rows here, as you see here. This is where y equivalent to y1. So now I ask you a question, what is the probability of x? I mean, how these intensity values are distributed at this row, y equivalent to y1. So you see that. So most of the pixels are dark, no intensity value here. So the intensity value is 0, 0, 0. There is a high intensity values here. It means the distribution is high here, high intensity values, and then there is no intensity values 0, 0, 0. It means this is how the pixels are distributed according to their intensity values. Okay. Similarly, if you take y equivalent to y1, then you see that distribution is something like this. The no pixel intensity values, slightly intense pixels, then no intense values, right? Lightly high intensity values, then nothing. So this is how the pixels are distributed according to their intensity values at this row, right? So now if I give the underlying distribution as this, I've asked you to estimate the probability of x given y equivalent to y1. It means according to this underlying distribution. I asked you to estimate what is the probability of x according to this underlying distribution. Will that be the same, both of them? Different, right? Because the underlying distribution is different, right? And the probability estimate will differ according to the underlying distribution, right? That's why, right? So we've been talking about the probability concepts from last 1 hour. Okay. So why is this useful? Okay. So can we take 5 more minutes? Is that fine? So
Yes,
to give
Yes,
sir.
sir.
some
No
logical
problem.
conclusion. Yeah.
Yes.
Yes, yeah. Good
Because you
going.
know that you might have already spent a lot of time throughout the day.
No, no, sir. Good
So,
going, sir.
okay, okay. So
It's all
that's
fine.
why, yeah. So we've been talking about the probability concept, probability, and only probability from last 1 hour, right? So why is this we are talking so much about the probability? How is it useful in the context of the machine learning or the data science? Okay, so let us take some motivating example and conclude the session. That gives you motivation to attend the next class. Otherwise, you may not attend. Okay, so I'm just kidding. Yeah, so here is an example of the classification problem. There are two types of insects, katydids or the grasshoppers. Okay, we have given the images of the katydids and the grasshoppers and the labels corresponding to them, to which class they belong to. Given a new insect, we need to classify whether it is a katydid or a grasshopper. We don't know what label associated with it. It's a new insect. Okay. So for any domain of interest, one can extract the features like the way I have mentioned, right? So we can extract the features like abdomen length, thorax length, whether it has wings or not, what is its color, what is the antenna length, what is the mandible size, what is the spherical diameter, what is its leg length, and so forth. Okay, just for the simplicity, let us only take the two features, abdomen length and the antenna length. So these insects are represented numerically on these two features, abdomen length and antenna length, and the corresponding class indicating whether it is a grasshopper or the katydid. So these are the 10 insects given to us. This is the 11th insect for which we want to make a prediction that whether it belongs to grasshopper class or the katydid class. Okay, so if I see the distribution of these insects according to their abdomen length and antenna length, this is how these insects are distributed according to their abdomen length and antenna length. So if I take more insects coming from the same distribution, it may look something like this. Okay, so this is how the insects are distributed according to their abdomen length and the antenna length. So now suppose let us take only one feature for the simplicity again. Okay, so let us only consider the antenna length. So we just want to analyze how the insects are distributed according to their antenna length. Okay, so you can see that according to the antenna length, most of the insects are here. And as you go this side or that side, it is slightly reducing as you see in this distribution, right? So this is how the katydids are distributed according to their antenna length. And this is how the grasshoppers are distributed according to their antenna length. So can I use two normal curves to summarize the distribution of the katydids and the grasshoppers like this? Can I use?
Yes.
Yes,
Right?
yes, sir.
So I can summarize them using the two normal distribution curves, something like this. So given this underlying distribution and given the new insect for which we know what is its antenna length, what is the probability that it belongs to katydid class and what is the probability that it belongs to grasshopper class? That's all we have to do. We have to estimate that and we have to pick up a class that maximizes the probability. So let's say that I have computed probability of a new insect belong to grasshopper class with its antenna length some L is equivalent to 0.8. And I've also estimated probability that it belongs to katydid class for a given antenna length L is 0.2. So which label would you assign? Grasshopper or katydid?
Grasshopper.
Grasshopper,
Sir.
because this has got the maximum probability, right? Right. So how to estimate this? Yeah, any query? Okay, fine. So given a new insect for which we know the antenna length is 3. So to which class it belongs to? We have to estimate antenna length 3 means here. You see that here this is the distribution of the katydids and this is the distribution of the grasshoppers. So to which class it belongs to? Higher chance
Grasshopper.
grasshopper, right? Suppose if the antenna length is let's say somewhere here, then
Katydid.
katydid, right? Yeah. So yeah, so this is the antenna length 3. You see the distribution. According to the distribution, there are 2 insects here with antenna length 3 and 10 insects, 10 grasshoppers with antenna length 3, right? So the probability of the grasshopper is 10 by 12, which is 0.8333. Probability of the katydid is 2 by 12, which is 0.166. So which label should we assign in this case?
Super.
Grasshopper. So let's take another. Antenna length 7. So this is the distribution, right? 3 katydids with antenna length 7. Sorry, 3 grasshoppers with antenna length 7 and 9 katydids with antenna length 7. So 3 by 12, 9 by 12. So which label should we assign in this case?
Candidate.
Candidate. Okay, so like this. So you got some motivation, right? Why we had discussed it. This all. There are a lot of other places we're gonna use, but at least some motivation, right? Yeah. So to summarize this, whatever that we have discussed so far, we have discussed some rules, right? For both discrete and the continuous cases. We have discussed the product rule. Product rule is this: joint probability is probability of the first event times probability of the second event given the first event. And then from these two, we have derived the Bayesian rule also. And there is another rule that you need to remember. This you might have known, right? Joint probability of the n events. Probability of x1. You're hearing some noise, right? My daughter is making some noise in the other room. Probability of x1 to xn. Okay, joint probability of n events. This is probability of the first event times probability of the second event given the first event times probability of the third event given the first two events times, can you tell me the next one? Probability of the fourth event given first three events, and so on. Can you tell me the last one? Probability of the nth event given first n minus 1 events. So this is, we call it as a chain rule. Okay. So that's all for today. If you have any queries, I can take. Otherwise, thank you very much and happy learning. Good night.
Sir, can you please share the recording link of these sessions?
Yeah, sure, ma'am. Daily I'm sharing. You need not ask.
Okay.
Say that